3.1. We're going to work on how to graph quadratics, and we're going to break it into very simple pieces. And these first two sections are very, very easy. So all quadratics are based off of the graph y equals x squared. So if you built a table and you had like -3, -2, -1, 0, 1, 2, and 3, and you wanted to figure out the y values, what is -3 squared? What's -3 times itself? +9. And -2 squared is 4. And -1 squared is 1, 0. And then the positive numbers yield the same squares as their negative counterparts. So 1, 4, and 9. To graph that, no. Well, this isn't what you're going to do. I'm trying to teach you how the graph is built so that when we change it, you'll be able to graph it without making a table. Because a table is kind of a pain. We don't want to be doing that every time. So the graph looks like this. It is a symmetric U-shaped graph, and it's called a parabola. Parabola. And lots of things are shaped like parabolas. Parabolas have this really interesting quality where if you shine a light or if you send sound towards a parabola inside that U, all of the sound is going to bounce off the parabola, and when it comes out, it's all going to cross through the same point. So, for instance, a satellite dish is shaped like this, and the satellite sends in a signal from the sky, and all that signal comes in and bounces off the parabola, and there's this little device. I don't know if you've realized this. There's a little device, and the sensor does not point to space. It actually points in to the parabola because all of these lines bounce, and they all land in the same place. So have you ever seen anybody at a sporting event who's holding that big clear dish and they're aiming it at the players? What that does is it takes all of this sound, and the sound bounces off, and then as it reflects out, the microphone is pointed in, and you can take this much sound and aim it into one little tiny microphone, and you can pick up sounds over huge distances. Glasses work the same way. Your glasses, so sunglasses are shaped like this. It's the same thickness all the way around. Okay, but reading glasses, or like my glasses, they're actually two parabolas of different shapes. So my glasses are thick on the edges and then narrow in the middle. That's not a very good example. Sorry. So my glasses are kind of that shape. The front is a parabola, and the back is also a parabola. And so when light comes in here, it actually spreads it out. Because I'm nearsighted. I can see up close but not far away. Yeah, so the middle one just goes straight through. That's a good point. So you can actually see this with my glasses. Do you see that halo that's around the outside of my glasses? That's because the light is hitting it and then spreading. So the dark area right here, it's not actually dark, but my glasses have taken that space and spread it out, and you can see that I am farsighted. So let's see yours, Daisy. Are you nearsighted or farsighted? So yours will be the same. Let's see whose prescription is worse. Let me steal your glasses. Anybody else have any? No? take your contact lenses out. So whose eyes are worse, mine or Daisy's? Or, sorry, Sadie. Her halo is larger than mine, so you're not a lot. Your eyes are just a little bit worse than mine. But Somebody who is farsighted, their glasses are shaped the other way. So um, they're thin on the edges and thick in the middle. So when that light comes in, what's going to happen? It's going to bend it in, and you can actually fry ants with their sunglasses. They're basically magnifying glasses. You know when you look at somebody and their eyes are huge because they have big glasses that magnify their eyes? They're farsighted. They can see far away, but they have a hard time seeing up close. Um, all reading glasses that old people wear are magnifying glasses. Okay, and the reason is your eye, the lens of your eye is actually flexible. It's called your cornea, and the muscles around your eye stretch and compress that lens, and that's how you can focus on things up close or things far away. If you're looking through a scope, you have to spin the dial, right? You have to focus it. A camera has to focus. So your eye can change the shape of its own lens. So your eye lens kind of looks something like this, and it can compress. I might even be able to do it. Let's see. Nope, it won't let me. So when you get older, your eye has a harder time changing shape. Like naturally, you can see far away, and to see up close, you have to work harder, right? But that cornea becomes more rigid, less flexible. And so by the time you hit, I don't know, 45 or so, it starts getting hard seeing up close because your cornea won't squish like it normally does when you're younger. So pretty much everybody has to have reading glasses at some point because their cornea just quits flexing. So that's why when your arm is not long enough to read anymore, it means you're old. It really just means that your cornea has become more solid. And you can still flex it a little bit for distance, but anything up close, you just need glasses. And as it becomes less and less flexible, you need a stronger and stronger prescription. So next time you're at Walmart and you see all the reading glasses, you'll see like 1.25, 1.5, 2, 2.5, 3, 3.5. That's how strong the magnification is. And the older you get, you have to get a stronger and stronger prescription. So parabolas are extremely useful. We use them all the time. A satellite dish is like a three-dimensional parabola. It has a parabola in the x direction, and it also has a parabola in the y direction. The nice thing is you can capture a lot of signal. If you just stood a microphone, like this microphone that I'm using right here, it will pick up my voice, but it won't pick up yours. If I had a parabolic dish and you guys were talking, I could bounce that sound off of the parabola and then into the microphone, and I could pick up anybody I wanted if I aimed that dish at them. I should get one. So, going back to this, we're going to look at the shape of a parabola according to the equation. Now, we've taken the equation and factored it and found where the parabola hits the x-axis. That was chapter 2. Now we're going to learn to graph the parabola according to the different pieces of its equation. So this one right here, the x squared parabola, is sort of the basis for all other parabolas. Okay, so I'm going to move that over. That's the original. Move this stuff out of the way. What if I had y equals 2x squared? That means I'm going to do the same list that I did over here. -3, -2, -1, 0, 1, 2, and 3. But now, after I do the squared, I'm going to double the graph. So -3 squared is 9. So -3 squared is 9, and then I take 9 and multiply it by 2, and I get 18. Okay. And then -2 will give me what? 4, which then gets turned into 8. And the next one would be 1 multiplied by 2 is 2. And then, of course, the other side is exactly the same. And if I graph those, let's Let's actually make these red. So I'm going to graph the new points there and right there. And then the other one's going to be like right there. How is that graph different than the original? Yeah, and there are two ways to describe it, and you actually did both of them. Good job. It's kind of skinnier and it's kind of taller. But where did the points actually move? Did the points move in closer to the y-axis, or did they stretch higher? They stretched vertically. So this graph is 2 times taller. Now, it kind of looks like it's 2 times skinnier, but we didn't move any of the points in. We moved the points up. And there is a way to move points in, but you're not going to see that today. So this graph is 2 times taller. Okay. What if I wanted y equals 1/3 x squared? What is that going to do to the numbers in this list? Well, 1/3 of 9, so here's my new y values. 1/3 of 9 is 3. 1/3 of 4 is 1.3 repeating. And then 0.3 repeating. 0, 0.3, 1.3, and then 3. So let me graph those. So here, 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 and here. How would you describe that graph? Which way? Vertically, right? You might say it's stretched horizontally or it's wider, but that's not what happened. The points actually were smashed vertically or compressed. So we would say that this graph is shorter than a regular graph. Okay. Now, I'm not going to be terribly technical on exactly if these graphs look correct. All you need to know is this one's taller, and you might say it's a little bit taller, or it's really, really tall, or it's shorter. And anytime you multiply by a number that is bigger than 1, you're going to make the graph taller. Anytime you multiply by a number that is less than 1, you're going to make the graph shorter. And then there's one other big change that can happen. What if I change this 2 to -2? What's opposite? The parabola is going to flip upside down. And now all my now everything is going to open down. So for 3.1, this is kind of our basic shape parabola. If I wanted to graph 6x squared, what would it look like? Taller or shorter? Taller. A lot taller or a little bit taller? It's pretty tall. 6 times taller. So basically, every one of those gets 5 more. And you don't have to draw this, but every single distance, then I would need 6 of those, which is way off the page. So 6x squared is going to be super tall, like that. Okay? What if I had -1/2 x squared? It's upside down, and it's squished vertically or shorter. So if this were my regular parabola, then my -x squared would be half as tall, something like that. Does that make sense? Okay. What if I had this? 4.3x squared. Taller or shorter? Taller. Why? that coefficient, the number in front of the x squared is called the coefficient, is bigger than 1. So it's going to be quite tall. Okay. What if I had 4/5 x squared? Squished. Why? It's smaller than 1. Is it really squished? No, why not? 4/5 is pretty close to 1. So it's not very squished. So if the regular x squared looked like that, 4/5 x squared would just be a little bit shorter, something like that. Okay. What about negative 9/8 x squared? Upside down. And it's taller, a lot taller? No, just barely taller than normal. All right. So in 3.1, I want you to do 3 through 17 odd. All right, get to work.